So hello, everyone. I am Mark Zimmerman. I'm a research fisheries biologist from the National Marine Fisheries Service, which is part of NOAA. And I live and work in Seattle, Washington. And I realized I'm probably one of the very few conference participants still stuck on Wednesday, December 1st. I will be your moderator today for Technology Innovations session number 2 at the Map the Gap Symposium 2021 Redux. I had to look up the definition of redux, and it means brought back, restored, referring, I think, to the Map the Gaps meeting we had earlier this year in January. So just as a reminder, we are recording this session. We have 4 speakers in the session, and each will be talking for about 12 minutes to allow for a few questions and a transition to the next speaker. Our first speaker is Neil Tinoff, the co-founder of ACUA Ocean, and he will discuss the use of technology as multi-mission platforms and how this can enable new financial models for funding research.
Well, morning and evening all. As mentioned, my name is Neil. I'm the co-founder of ACUA Ocean. Talk a little bit about scalable and sustainable ocean technology and how this can bring up create some new opportunities for research and new funding models. So I am going to do a little bit of preaching. I know we're all passionate about the oceans, but really about how important the oceans are from a holistic approach. So one of the things is that oceans really is tied to human health. COP26, there's a lot of good stuff came out of COP26 around the oceans and around nature-based solutions and how the oceans will help play such an important part in regulating the climate and climate change. So to date, it's absorbed about 90% of excess heat generated through anthropogenic causes. It's also 83% of all carbon cycle passes through the oceans, and about 30% of all anthropogenic carbon has been sequestered by the oceans to date, and as well as providing 80% of life is found in the oceans. So the oceans are really a key part of our society. It's huge with regards to it feeds around about 3.3 billion people, 80% of global trade. And in the UK, something like 97% of all financial transactions go through submarine cables. It also employs a lot of people. And 250 million people are directly employed by the blue economy, and millions more are employed indirectly through fisheries processing and other activities. In total, the blue economy is worth around about 2.5 to 3 trillion dollars, which would be the 7th largest economy in the world. And this is really expected to grow to about 5 to 6 over the next couple of years. So there is a massive financial opportunity within the ocean sector. But what is quite disappointing is when you consider that this huge opportunity is how poorly we really look after the ocean. So currently only 2.8% of the ocean is fully or highly protected. Now, drawing lines on a map and saying it's a marine protected area has some benefits, but it's been proven time and time again that it's got very limited benefits. If we want to get the most out of our marine protected areas in the ocean, we need to actually do a lot more about enforcing it. So the challenge is, so it's been set in the SAMs 30 by 30, UN 30 by 30. We're going to try and protect 30% of the ocean. But to do that will require a compound annual growth rate around 35%. Now, that is a really rapid growth rate. And when you think about the technologies that are going to be required, if you want to get the platforms offshore, they're going to have to increase substantially. In the UK at the moment, in the territorial waters, we use probably about 1 frigate at a cost of about $1.6 billion for a single frigate. And that's meant to cover an area of about 4.5 million square kilometers. It's a huge amount of area to cover with a single vessel. So there has been some positive movements, again, in the build up to COP, around 70 countries committed to protecting 30% of their territorial waters, which is a great start, and it's showing a great momentum. But also when we're taking a look at, again, on the holistic approach, because the oceans are so interconnected, you need to take into consideration the areas beyond national jurisdiction, which actually, that's about 60% of the oceans. So again, just the sheer vastness that we're going to have to do to be able to reach these UN 30 by 30 goals is great. And one of the biggest challenges, as we all know, as people recently be in the research and science sector, is that there's this massive funding gap. So what you see here is UN Sustainability Goal 14, which is life below water, which is the one that applies to the oceans, is probably one of the least funded gaps or strongly misaligned gaps, and most strongly and least strongly aligned. So to achieve sustainability goal 14, they estimate requiring about $175 billion per year by 2030. At present, only 25.5 billion is spent annually. And just to put that into perspective, global fishing subsidies, which about 90% are focused on increasing catch, so not about doing things more sustainably, but actively encouraging overfishing, and things like providing diesel to encourage fishing in further offshore or further away from your territorial waters. That is actually 35 billion. So $10 billion more is spent on global fishing subsidies than is actually spent on UN Sustainability Goal 14. And this results in a funding gap of $149 billion per year. So when we think about actually what is part of the driver of this, and it comes down to a couple of things. Again, operating offshore is really expensive. It's 2 to 3 orders of magnitude more expensive than if you were doing similar to activities on shore. And it's a bit of a theory of the commons, that this is a global space where there's actually very few people who are actually regulatory monitoring it. So people are kind of free to abuse and take advantage of it. So if we want to move towards a more sustainable ocean, we're going to have more presence offshore. And you can look at this funding gap as this is a major negative, but we can also start to look at it as an opportunity, because as the pressure at the UN Decade of the Oceans, COP26, COP15 next year, which is focusing on biodiversity, starts to shine a light about how important the oceans are, this funding gap will be shrinking, and countries and governments, NGOs and financial institutions, impact investors, that will be putting money towards the ocean. And this creates an interesting approach. And so to bring this back into the ocean mapping community, it's really taking a multi-stakeholder approach, because there is a definite trend today in these days that we've moved away from the era of data is key, data is king. Everybody, a couple of 5 years, 10 years ago, data was everything. If you look from Facebook, it was a data play. But now we're looking at what everybody's looking for is insights. So how do we turn what we're doing as ocean mappers into insight that can provide value across this growing opportunity around marine monitoring and protection? And some examples here that are provided is around things like habitat mapping. So when you're doing your fisheries and you wanted to do your MPA protections, it's identifying where you want to put your resource, or where to spend the effort and the money to protect and monitor, where is adding the most value. To do that, we need a huge amount of habitat mapping. And also, so the other challenges around monitoring protection is things like bottom trawling. So it's just been released in a paper in Nature earlier this year that bottom trawling releases around 940 million tons of carbon from the ocean seafloor every year. That carbon comes from the sediments, it gets released into the ocean, and it prevents more carbon being sequestered from the surface. So by being able to understand where bottom trawling is happening, being able to detect it, being able to collect evidence of bottom trawling for prosecution is kind of a key aspect. And another very hot topic at the moment is carbon sequestration. And within the blue carbon movement, one of the key focus areas is around seagrass mapping. Now, what is quite interesting about this, again, is if you take it from why we actually need funding and why actual scalable solutions is quite critical, is that these are not just once-off surveys. These are multi-year surveys. You want to be able to track the changes of the habitats. You want to be able to track the changes in bottom trawling. Are you deterring behavior? Are you is the seafloor managing to recover? And you also want to be able to track the seagrass mapping. Is the seagrass recovering? Is it able to sequester more carbon? So therefore, we actually need scalable solutions. And the real challenge here, well, the real opportunity here is, again, it's not one solution will fit all. It's being able to bring in these scalable solutions from every area, from satellites, and bringing in the benefits of satellite technologies, how they can actually do a lot of monitoring on a large scale really quickly, to Argo floats, wave rider buoys, all of these type of platforms collect data. But there's also an opportunity around here about, again, on the monitoring protection side, if we're going to be putting platforms off to try and protect and monitor the marine protected areas and these growing marine protected areas, what is the data can we collect? And this becomes quite critical, because it means that we have more platforms offshore, means more data for better informed decision making and better science. And this has really been driven by a couple of things in the last couple of years. There's a huge advancements in robotics. So we're moving away from vessels, even just uncrewed vessels. We're moving away from that towards things like swarm operations, where there's a higher level of autonomy on these vessels. This brings about scalability. So going from a manned vessel to a USV brings about the opportunity of decreasing the size of the vessel, but you still have the high cost of personnel. And again, if we're scaling out to protect 30% of the ocean and we're scaling out the resources needed, we're not going to have enough personnel to actually operate all of these platforms. We need to go towards AI and robotics. Again, also the amount of data collected. So more platforms means more data. So being able to process a lot of this data on the edge, on the platform, do a lot more rapid processing, move people from in the processing loop to on the processing loop to supervise and focus on the small challenging areas is going to be absolutely critical. And this is something that Map the Gaps has already experienced through the UTAS project, Unmanned Uncrewed Transatlantic Survey project last year, where they managed to get the processing time down for 20 days of multibeam data processing, significantly using things like Telegram Mirror AI. There's also opportunities around here around alternative fuels. So one of the challenges, again, around uncrewed surface vessels as a platform is when you're using diesel and diesel generators, they need oil and filter changes, they break, and they do have lots of moving parts, so they tend to fail more regularly. Alternatives at the moment around wind and wave power, solar power, and these are really great platforms and really scalable solutions. One of the challenges is that they do not necessarily have enough power for a wide range of sensors. So again, if we're having these platforms offshore, we should be collecting as much data as possible. Alternative fuels such as hydrogen and using fuel cells, which are only require things like a visual inspection once a year, open up new opportunities for long endurance platforms. And then also satellite data. This is not only satellite data from a Earth observation platform, but also from a communication perspective. One of the, again, challenges of USVs and platforms offshore is if you have all this data, how do you get it back in near real time for better decision making? So these are the enabling technologies, and we see a great opportunity from this. So this is the unashamed company pitch and what we're really doing about this. So what we're doing at ACUA Ocean is we are developing hydrogen-powered uncrewed surface vessels. Endurance of around 70 days of 5 knots, 500 to 1 kilowatts of payload power in addition to that. And the idea is, again, is that we want to be doing this monitoring and protection side of things, but we want to be able to provide the platform that has the power to feed it back into the scientific community to make better informed decisions. And this comes from, again, things like seagrass monitoring, detection of bottom trawling, habitat mapping, but also being able to use data through the water column, being able to provide surface information and the likes. So there's a holistic approach that we see and a new wave of technology that's going to enable new financial models, drawing in investment. These are commercial opportunities that can have a huge benefit for the scientific community. So that's about it from my side, and I would love to get people's thoughts on how they could see using a platform if they had it, these platforms offshore. Yeah, so happy to take questions.
Well, thank you, Neil. I think we have time for maybe one quick question. Let's see, I'm not seeing any, so potentially people can contact you by email and interact with you directly later on.
Perfect, sounds great, thanks.
Okay, thank you. Let's see, are you able to stop sharing? And Danny, are you able to start sharing? Okay, our second speaker, Danny Neville, is the Managing Director of Spatialnetics Solutions, and he will show us how lightweight microservices can address the challenges of automating hydrographic workflows.
Thank you. Hi, everyone. As I mentioned, my name is Danny Neville. I'm from a company called Spatialnetics. I'll be talking about automating the ocean mapping workflows with microservices and virtualized applications. Oops, sorry about that. Move this out of the way. So it will be a technical discussion on these topics, but also try to tie them into some practical examples. Now, as global efforts to map the ocean floor accelerate, marine data collection is becoming more decentralized, more autonomous, and more remote. Now, when considering automation, we can really separate that into two parts. Platform automation, such as the control and handling of robotic platforms in the physical world, but also workflow automation, a broader concept of automating any task or process that a human is doing. For this talk, I'll be focusing on the workflow side of automation. Now, no matter what your specific type of operation, there are numerous benefits to automating your workflows, such as having more immediate feedback, things like faster delivery of your end product, but also with intermediate products, you can have better coordination. You also can aim for increased productivity by reducing errors from the manual steps, being able to focus time and on analysis and bigger picture items, and also being able to batch your interactive versus non-interactive time. Now, the concept of workflow automation is not at all new, especially in the world of surveying. For a long time, people have been using tools such as batch scripts or glue programming with Python to make their lives easier. In addition, across the different software and hardware vendors, there's a wide variety of options and approaches for leveraging their functionality in an automated way. Add to that the growing number of new technologies and tools, it's really an exciting time to be working in this area. However, with all these options, there are also challenges, starting with the current state of your hardware and software, as well as the momentum that might be around your current workflows. There are also resource barriers in terms of IT readiness and flexibility to change, development capability, and incompatible systems. Add to that the domain-specific challenges of the marine environment, such as large data volumes, remote operations, or completely disconnected operations that have no access to cloud processing. However, we can address those challenges by using some traditional change management techniques. Things such as breaking down larger systems into smaller pieces, lowering the learning curve, doing incremental change, and leveraging existing tools and knowledge. One approach to help with that is by using microservices. They can be used to facilitate the decomposition of the larger systems, allow you to apply small targeted functionality, and stage things for incremental change. In addition, we can maintain functionality by using virtualized applications, with a large portion of our core processing capability coming from traditional applications. By virtualizing them, we can also increase their scriptability and remote access. But what are microservices? Well, a microservice is an architectural style that structures functionality as a collection of small services that are also loosely coupled, independently deployed, and organized around operational capability. The diagram on the right illustrates a traditional monolithic approach with a single application containing all the user interface, storage, and processing logic in one unit. We can compare this to a microservice approach where functionality is separated into independent services. This makes it easier to change components, add new capability, as well as work across distributed systems and into cloud processing. Now, going from concept to practice, Spatialnetics has been building custom microservices to help address specific gaps in workflows and take incremental steps for more automation. Although we are currently building these as custom services, we are working towards offering them as off-the-shelf components early to mid next year. Now, jumping into some specific examples, we can start with a basic single service used for doing file conversion. In this case, going from another data format to the GSF format. This is a common requirement for getting data into a format that can have further processing in applications such as Chimera. We start by using the service as a command line tool and simply providing a single input file to be converted. This could be used as part of a larger script or run as a component in a serverless platform such as AWS Lambda. However, by itself, it is not much of a service yet. To make it more of a service, we can change it so that it monitors the directory and runs continuously. Each time a new file shows up in a directory, it will convert it and produce a new file. We want to also control and monitor the service, so when we start it up, it's also creating a small web server. Now, all of the microservices we are building can be accessed via command line, a web-based user interface, and have an API for further integration and control. Looking at the web UI for this microservice, we have 4 tabs. We have a status tab just showing specific information about the running microservice, a host tab with information about the host machine, such as memory and percentage of CPU usage for the current service. We also have a control tab for manual control of the service. And lastly, an API tab for a quick guide to available API functions for that specific microservice. Our next example of using a single microservice is a real-time converter. In this case, a client needed a custom driver for an INS system with monitoring and rebroadcasting to an acquisition system. Now, this is a good example of a targeted microservice being used to fill a gap in a much larger system. For this project, there was also a need for a standalone GUI application that could be used to set up, control, and monitor the convergence surface. The service API was used to provide the backend functionality to the application. With that application, you have access to status information, configuration, as well as testing information for QA/QC. So what kind of things can we do with microservices? Well, a lot of what we've been doing is building things fall into the categories of core data handling or data sanitation or janitorial tasks. So format conversions, metadata creation, or just things like file name consistency and making sure your time and geodetic matches, and cleaning out incomplete files. Now, going further into more primary processing product generation, we tend to leverage capability from third-party tools and applications rather than building that ourselves. Now that we have looked at running single services, we can look at using multiple ones together as part of automating a larger operation. In this example, we have a simplified workflow where we are looking at the path for producing SBET files before going into Chimera application for final processing. To start automating this, we can use a microservice to first collect and copy the raw data. That then communicates for the actual batch communication with a microservice built around the POSBAC batch command line tools. And then finally, there's a third service that is monitoring the output and staging the SBET files for consumption by Chimera. Now, what is the advantage over using a single batch tool or using a standalone script? Well, the first advantage is the loose coupling. Only the external connections are required. This increases the portability, and we can move each service to a local, remote, or cloud host. It's also easier to test, and also easier to swap out the component with a different one as necessary. Now, we also have built in a web UI and external API that allows easier monitoring and integration into larger systems. Now, in the last example, we use command line control of a third-party application to produce the SBET files. The other options for controlling applications are either directly with an API, with internal application automation, or with external application control, which can have more setup requirements but allow a wide range of automation options. Now, another key part of automating third-party functionality is moving those applications to a virtualized platform, which can then be managed and controlled by another specific microservice. Now, to put all of this together in a final example, we will look to add some further automation to the workflow, focusing directly on the primary processing. First, if we take the Chimera application, we can put it in a cloud-based virtual machine. This will now give us global remote access to the application and get us fast access to some cloud storage. Now, because a GPU-enabled cloud virtual machine can be a bit expensive to run, you probably don't want to leave that running 24/7. So we can add a VM control microservice that can create, turn on, and turn off the full VMs as needed. We also want a microservice that monitors when new data arrives in our cloud storage and coordinates with the VM control service to activate the full VM. We're then ready to do the actual automation and use microservices for project creation, adding data to your project, and creating surfaces. This is all done by the macro recording control. Now, with our applications virtualized, we can remotely access them using any web browser, and we can manually launch and control the applications directly. But by adding the macro recording control, this allows us to leverage GUI test frameworks to play back pre-recorded operations for things such as creating those projects or adding the data. There are both open and closed source commercial options for the GUI test framework, many with advanced functionality for not just recording mouse movements, but actually using image analysis to intelligently process text and dialogues. With these automation services now in place, we can also consider options for scaling the workflow. The first option to scale performance is by dynamically moving your application to a more powerful machine when needed. Going a step further, you can scale to having simultaneous machines running in parallel to produce parallel outputs. This could be used for things such as cumulative versus daily projects and services, different output products altogether, or even different processing settings and scenarios. Now, however, there's important licensing considerations when attempting to scale commercial applications this way. At a minimum, you need a floating license structure where individual licenses are not tied to specific hardware. To do the parallel operations, you either need a large number of temporary concurrent licenses, you need a large pool of available licenses or an option to temporarily scale to multiple concurrent licenses. I'm hopeful that the software vendors will move towards providing some of these options for increased scalability. Now, as we improve the amount of automation in our workflows, there's also a need to increase the level of intelligence they have. AI will play a clear role in this. However, even without AI, we can make our workflows smarter by adding some simple tools to the mix, using things as automated sounding density calculations, standard deviation, or comparisons with reference data. By creating these intermediate products can allow the automated workflow to be smarter about what's happening, either stopping the process altogether or choosing alternative options in the workflow. Combined with the scaling to multiple parallel outputs, this applied use of microservices and virtualized applications can further move us towards our original goals of more immediate feedback and increased productivity with optimizing human time. Thank you for the opportunity to talk today, and please let me know if you have any questions, and please get in touch if you'd like to discuss any of these topics further.
Well, thank you, Danny. We've got a pretty good audience now. Is there anyone who has any questions for Danny? Let's go ahead and type your questions into the question and answer box, please. Okay, I'm still not seeing any questions, but people can get in touch with you directly later on, perhaps. Thank you very much for your presentation.
Thanks.
Satish, are you able to share your screen?
So can you start, Mark?
Yes, I'm sorry, I forgot to read your introduction. It's addressing the navigational issues of deep sea mapping. Satish Ramachandran, the Chief Technology Officer of Robotniks, will talk about the use of spare long baseline arrays. Take it away, Satish.
Thanks a lot, Mike. Thanks a lot. Very good morning, good afternoon, good evening to everyone. So welcome to Map the Cap Symposium. So it's been a pretty much happy day for us to showcase the development we are carrying on. So this is Satish Ramachandran here. I'll be presenting how the sparse LBL and is being utilized to improve the navigation as well as data processing capabilities of bathymetry survey. So we are actually demonstrating that capabilities in a scope called SRRS. So SRRS means Subsea Residential Reference System. So we shall get in with a quick introduction of what Aerobox 10X as a company is, and then we'll showcase about the development we are actually working at the moment, and what are the capabilities and what are the simulation models we are able to demonstrate that spatial LBL for an hydrographic and bathymetric survey. And finally, a real-time demonstration has already been carried out by iframe. So the part of the agenda for our discussion for next 15 minutes is going to be that. So let's get in. So Aerobot is a company based in India, so and also in Canada. So we focus mainly on unmanned systems, automation, robotics, and we just started in 2016, especially on Canada, to concentrate on Arctic mapping and oceanographic solutions. So we vision ourselves to really play a critical role in less carbon footprints operations and to be a survey company, a leading survey company by 2030. So we currently transform and work with Indian oil and gas industry and also support the different oceanographic and hydrographic research communities across India. So some of the kind of the response as well as accolades we have received is, one of the biggest thing is we won our cloud autonomous framework has won the Reboot the Ocean challenge organized by United Nations in 2020 for under the mapping the oceans category, where we showcased how a low cost autonomous framework could really help and deploy heterogeneous systems in the underwater to carry out the mapping so that we can achieve the seabed 2030 challenge as soon at the earliest as possible. And we have been accepted and we have been appreciated for showcasing our framework, and that is where we started. And also we are also working on a kind of a platform called WooSci-Fi, which we will be showcasing later on the part of the slides as a simulation tool. So we focus mainly on as a simulation as well as a development in integrating sensors as well as autonomy. That's our core use case. And we recently also presented at the MAS 2021 conference showcase where we talked about how a simulation, autonomous simulation for offshore applications helps in planning and control session to help to achieve the best data as well as how the data can be acquired properly as well as can be utilized for better processing. So it is headed by Michael King, Ocean 20 from Ocean 20. So these are basically about us, and let's get into some of the details of what the topic we will be talking. So we are currently will be presenting mainly on spatial LBL. So with nearly 17 years of offshore experience, I have deployed a lot of long baselines in my offshore work, but there is always a challenge that deploying is going to take a lot of time, and localizing with multiple transponders to get a position is going to be a real cumbersome process. So what we have been researching in the last 2 years is how we can able to achieve, even in terms of a defense application or in research or in the commercial, how in any kind of underwater vehicles is going to be an ROV or an AUV or a USV can get more better positioning, can get more better navigation data, and which in turn helps the processing to get completed quickly. So that is what the real interest we got, and we have really spent so much time in the last 2 years to understand how really the SPAS LBL array has been really the game changer. So to give a quick overview of what is an LBL, so long baseline is basically for any kind of challenging work or any kind of references on the seabed, the industries will deploy multiple transponders at an equal spacer along the line to carry out any kind of operations, for example, like metrology or any kind of out of station survey or any kind of seabed construction work. So it is really impossible to get the exact position. So we will try to create an array of localized point, and we'll try to calibrate the transponders deployed with the fixed process of calibration. And finally, once the calibration gets over, we'll get the ROV to carry out ROV or any kind of AUV to get to carry out the operation on the area of the array. So which will really improve the navigation as well as the vehicles movement data, vehicles maneuvering. So that in turn helps the multibeam data to get acquired, timestamp, and also gets to the final processing stage very easily. Because in the last few slides, when Danny was talking about the AI, definitely AI plays a very critical role in the multibeam data bathymetry. But more than that, there is also, along with the AI, navigation also add up with that. So all this data can create the process mode quicker and also solves the data for the final delivery. So the LBL is basically deploying multiple transponders, but SPAS LBL is, instead of deploying 10 transponders in the seabed, now is going to be only 2 or 3. So it has really come down to a stage where you don't need to deploy a lot of transponders to carry out the operation in the seabed. And why specifically for bathymetric survey is we are deploying ROVs, we are deploying AUVs, or we are deploying vessels to carry out a multi-beam of carrying out high resolution seabed mapping. So wherein the data are getting recorded, and the INS data is to be very, very important, and all the data on the seabed reference to carry out is going to be very, very good. So in order to do that, when you deploy the vehicle gets localized. Instead of 5 or 6 reference, now you just need to carry out to 3. But the only thing is you need to have a very powerful subsea vehicle INS on the vehicle. So the INS plays a very critical role. Is going to feed the information to the transceiver, and the transceiver pings to the acoustic transponders to get their reference locally, and the error gets nullified along with the INS, and that's where the baselines and all the reference points are calculated. So pretty much actually when we carried out the research, we understand that there is a huge requirement of the subsea readiness reference. We thought like the first primary thing where we put up ourselves to work is the position of underwater vehicle for 3D bathymetric survey. So we will be talking about a lot of use cases. Like one of the use cases, iPrimer carried out a similar kind of deployment with the help of Blue Ramses transponders. So Ramses transceivers and other Canopus transponders. So they have very much achieved the process very quickly, and the bathymetric data is so clear, and they have reduced the processing time to nearly 40 to 50% of time. So that really gives us a very clear sign. And then we started researching in deploying the transponders, how to deploy the transponder for what kind of operation, and how the bathymetric survey for which area we have to carry out, and how the array plan should be coming, and how the slamming should happen, and how the vehicle should understand slamming, something like that. We actually took ourselves after discussing with the OEMs, we could able to understand that. But the bathymetric survey is one such application, but mostly after that, we have been very much concentrating on the energy sector, because in the energy sector, we have a lot of applications from construction to asset integrity to a lot of things we need. And especially for DP reference also, this kind of residential reference is very, very critical. So this is kind of a one kind of a deployment example, like when the vehicle goes down with an INS and a transceiver, what exactly need, you could just see that spatial bill is just only 3 spatial bill, and certain OEMs are challenging that you can need only 2. Some are certainly challenging to have only 1. But we're just not going to talk about that, but we are just going to only characterize that what is the minimum requirement of deploying to get a better position is when you just have your AE or an ROV project or an ROV system to go down to carry out the mapping or something like that. When you need to have a reference, sometimes more than the USBL, LBL is very, very accurate and can really solve it very easily. And every system on the vehicle will have a transceiver on board which talks with the transponders, and the transponders are deployed first, and then we'll have to carry out a calibration of that. And that calibration really helps. And that calibration is localizing the position where it is, because since we are going to talk about an accuracy level of in terms of millimeters, so the position of the transponder is very, very critical, and those positions are being referenced from the USBL fix and then compared with the transceivers, as well as talking with other transponders where we just have multiple types of calibration to be followed up. And once the calibration is over, and if we need to, there is always a question that when the vehicle moves from one point to other, it's a traditional conventional process is pick up the transponder and deploy it in the next location. So here the good thing is you don't need to do that, because INS is going to help you to achieve and pick up the transponder and put it in next location where you need to carry out a thing called SLAM calibration. It's just a fundamental robotics concept, SLAM, simultaneous localization and mapping. So in any chances in a conventional way where we have to pick up the transponders and move to a new location, in this one you don't need to do that. It's all happening, everything on the seabed, where the vehicle itself can push from one location to other. But if the situation comes, if it's going to be an AUV survey, you can always expand the AUV survey to a level, because currently transponders are very much able to talk between 2 kilometers. I'm just saying, like max, and is also having a maximum range from 2 to 3 kilometers, but I'm just saying the worst case is 2 kilometers. So it is going to give a kind of an area of 5 square kilometers of an area where you can carry out a survey. So in any kind of the vehicle, transceiver gets also the information from the INS, and also they just talk together, and they will be able to localize it and able to finalize the position easily. But the most important thing of the INS is you need to have the aiding. You just need to have the pressure sensor aiding, the TVL aiding, and those kind of things is also critical. So this is one part of the platform where we simulate the information and we showcases, and we have to really thank the Professor Dr. Benjamin and Dr. Hendrik Schmidt and Dr. Paul Newman. So we have really taken decades of experience to bring in a platform called MooseAP. So where we actually, as a company, we utilize this framework to build up our development and also bring in more new innovations, like how the residential can be used in multiple applications. So this actually is our critical tool, where we also have videos, as well as we also have libraries available, which can be used as a part of a research program. We also showcasing this with the hydrographic community across India and other places where they can utilize this and carry out the behavior modeling, and also how the bathymetric changes with the navigation data, and how the data is going to be, how the critical data helps with proper time stamping and everything. So we're not going to talk more on this, and this is something we carried out a simulation which is very much available on the YouTube, as well as we just have the whole framework development ready. If your research is requiring that, we are also happy to help. So what we carried out the simulation model is how our A10 autonomously taking action development framework utilizes the reference system from the 3 compacts or 3 transponders deployed on the seabed to carry out a bathymetric mission. So we simulated and we carried out how the continuous acoustic measurements helps them to improvise the bathymetric data, and how the position observation is helping them to achieve the final completion of the survey quick time, so that they could be able to bring in more accuracy. So this is something we just developed with the help of an autonomous framework, and also we foreseeded this to certain residential kind of applications as well. So this is kind of a platform where it's just can be utilized and it can be expanded, because SPAS-LBL is just kickstarting in commercial as well as research applications. So it's high time that we started using them in many applications, so it gets the job over, and we can also reduce the amount of time in the processing. It can definitely is making a lot of changes on that. So SLAM, we already discussed. SLAM is going to happen only with an INS on board, and also an INS which should be very powerful, and the INS should be connected with your LBL transceiver, so that all the information can happen and the processing gets over through the INS, and the final data is being sent to the surface. So the next part of few minutes, I'll be talking on this real-time deployment. This is not from us. This is from iFramer. They deployed an use case on the vehicle in their Ramses, integrating and utilizing a SPAS-LBL, and they have very much achieved a very, very high accuracy. And along with the Ramses, they connected the fins and the DVL. So they are able to achieve and carry out the operation very quickly and very efficiently. There is I have just shared a link here. You can always go through that and you can understand more. And this is what just I'll be talking more, because you can understand the calculation model. So we like to thank Xblue for this, because they are the courtesy people for this. And you can see that all the filterings, final position, everything is being calculated. And finally, along with the Kalman filter and SLAM, you could be able to achieve the highest accuracy what you would like to get in finally. So there a lot of ejections is happening over here, and a lot of ejections happening due to USBL, the position, the error noise filtering is certainly been taken care, because there is no need from the surface to send any communication. It's all happening only in the seabed to finalize the position and send it back the updated results. So this is the pretty much from the Xblue. So this is the final calculations what they carry out. So this is the kind of the model how they have carried out the survey, and the kind of Xblue's plan of arrays just deploying 2 back-to-back kind of canopus transponders to carry out this operation. So they have actually given more information how this really helped them to achieve quick processing as well as able to get the results better. So I just would like to thank Map the Gap Symposium, because I'm done with that, and I'd be happy if we have any kind of questions to us, and we are very much happy to reach us for any kind of engagement as well as any kind of simulation requirements. We are happy to help you. So back to you, Mark.
Well, thank you, Satish, and so glad you were able to join us and make your presentation. It's very interesting. Does anyone have any questions for Satish? This has been a very quiet group. Okay, I don't see any questions. Thank you, Satish. And I think we need to move on to our final speaker, Lachlan.
Thanks, Mark. I'll just get my screen up now.
Okay. Lachlan Hurst is the Technical Delivery Manager of Frontier SI. He focuses on the processing, management, and visualization of big data. And it looks like you're ready to go.
Yeah, thanks, Mark. So you've already handled the introduction for me, so I don't know if there's much more to say here. So I work for Frontier SI, but it's important to note that I've been working pretty much full time with the Oz Seabed program that's run out of Australia for the last 3 years now. And the presentation I'll be going through today is on QACS, which is a tool for the automated quality assurance of bathymetry data. The story of QACS goes back to 2019 in a workshop we had back then. And the nice thing about workshops in 2019 is that we actually had them in person, which was really fantastic. So we had a great group of experts from around Australia and New Zealand all come together in one spot. And to top it off and make things even better, we had some representatives from NOAA and CCOM fly over and spend not just the week of the workshop with us, but also a month sort of to spearhead some initial developments that we took on as well. Giuseppe Tyan, if you ever see this recording, thank you very much for coming over back then, and hopefully one day we'll be able to catch up in person again someday. So there was two aspects to this workshop. One is that we needed to learn a lot about what tools were out there to do quality assurance of bathymetry data. And in that first week of the workshop, we actually absolutely grilled Giuseppe and Tyan, and they were able to bring in a bunch of other representatives from NOAA and CCOM to go through the very significant body of work that they'd done on looking at the quality assurance of bathymetry data. But internally at AusSeabed, we also needed to sort of get an understanding about what needs the AusSeabed program had itself when it came to quality assurance as well. So we gained an excellent understanding of what tools existed already, and we also developed an idea about what we needed. And from that, we could sort of start to line up what existed and what gaps there were. And from that, we sort of came up with this bit of a concept as to what we wanted our quality assurance tool to be. We wanted an automated tool that would allow us to go through and specify multiple files that we wanted assessed, and we wanted to be able to specify multiple checks to be able to run over each one of those files. We knew a lot of work had already been done, and a lot of it was open source, some of it was proprietary as well, but we wanted to leverage those tools wherever was possible. We had a number of participants in that workshop that came along with bits and pieces of code that they'd already written. So maybe it was a file parser for GZ files, or maybe it was something that did a quality assurance check for this specific thing. What we had is we found that there were sort of like bits and pieces everywhere, but trying to string them all together to work in a more seamless sort of automated fashion was a bit of a task. So we wanted something that would allow these smaller sort of modules to be integrated within a larger framework. Operation in batch environments. So Danny made me think of this one during his presentation. So he had like an excellent, I'm going to call it a workaround, sorry Danny, for driving some of these applications that just don't provide a method to run them in a batch or sort of headless way. And that was to drive them using some GUI test tools, which I thought was like a really great solution for that problem. But ideally, these tools like QACS and a lot of the other bathymetry processing software would provide a method to operate in a batch mode themselves natively without us having to drive it through some sort of GUI driving tool. Last but not least, open source. So a lot of the tools from NOAA and CCOM, well, all the tools from NOAA and CCOM are open source. We wanted to follow that pattern as well for a large number of reasons. So that's the concept, and that's how it was back in 2019. Skipping forward to what is almost 2022 now, it sounds a bit scary. This is what we've got. So if we run through the user interface, and it's deliberately quite a simple sort of user interface to step through. We've got step one, you'd go through and you'd say, all right, I've got a collection of files which I want to pass through some bathymetry quality assurance checks. So we're going to go through and we're going to drag and drop a list of the raw data files, so your Kongsberg all files, your GSFs, that sort of thing. You might also have some gridded data products, so your TIFFs and your bag files, they can also go in the survey digital terrain models there as well. Next step, we're going to ask you for some input parameters to support these checks. So for example, if you were running a density check across a digital terrain model, so you want to make sure that the number of soundings per grid node is above a certain threshold, we're going to need to know what that threshold is. So here we're saying, all right, the minimum soundings per node is 5. So the check needs to know that information so that it can pass or fail each grid node in the actual check implementation. Some of the other checks, input parameters get a bit more involved there, as you can sort of see. Once you've gone through and defined all your parameters, it then gets much easier because you can just click the go button and it'll run through and process all the input files that you've specified across the input checks that you've specified as well. So that'll run through. Sometimes it can take a while depending on how big your data sets are. Once it's finished up though, you'll be presented with results formatted in a few different ways. So underpinning all this is a sort of data structure we refer to as QA-JSON. There's a bit more on that in future, but I guess the idea of Quacks presenting quality assurance check results was to keep it nice and simple and lightweight and allow the user to quickly identify files that were failing quality assurance checks, and then also identify what components or what areas in those files are actually failing the QA checks. So there's some pretty primitive sort of visualization tools in there that will say, for example, you're looking for holes in your data set, it'll sort of extract out the outline of those holes and present them in a little map widget and that sort of thing. It'll present some summary information as well, telling you how many nodes failed a density check, for example, and a few other bits and pieces of metadata as well. The intention here is to not really replace like GIS capabilities that you'd find in something like Keras or ArcGIS or QGIS or whatever your preference is. It's more to sort of supplement those. If we have a look under the covers of Quacks a little bit, I guess, this architecture, you can sort of relate it back to the screenshots I had on the previous page. So if you look on the left, we've got the input files, which the user needs to go through and specify. We've also got that list of input parameters, which are required by each one of the checks. So what Quacks sort of does is it provides that layer that allows, it gives the user a user interface to go through and specify the input files and the input parameters. The actual implementation of each check lives in what we call a Quacks plugin. And here we've got 4 listed. So I've got Mate, Embezz GC, Finder GC, and QC tools. So these all sort of plug into Quacks. And we use this data structure called QA-JSON to sort of communicate between the user interface and each one of the check implementations. Quacks is also the thing that handles the processing and the scheduling of the processing jobs that each check undertakes as well. And when the process is completed, we can visualize the results, and that's obviously something that's provided by Quacks as well. So I mentioned QA-JSON a few times now. So what actually is it? It's, as some of you may be aware, it's a JSON-based file format, which is sort of a cross between something that's potentially human readable, but is definitely machine readable. So that's what we're sort of going for there. You could read it, but ideally it's going to be the machine that's reading this information for you. What it does is it's really just a formalization of the check data. So in the user interface, you specify what input files you want to run through these checks and what the parameters are being fed into each one of those checks. When each check's run, it's going to produce a bunch of output related to each one of those checks. QA-JSON it's the data structure that defines where those bits of information lives in a nice sort of standardized way. So things like input files, input parameters, and the outputs, whether or not a check passed, whether or not a check completed execution successfully, and is there like a little bit of like summary geospatial data that we can use to sort of help the user pinpoint the locations where problems were occurring. As for the checks and the check tools that we've got in there at the moment, and this is obviously all still a work in progress, I've got many big ideas and we'd love this list to be continually growing over time. To start off with, let's talk about Mate. So Mate's multibeam acquisition and tracking evaluator. And it implements the checks that would typically be run on the raw data format, so the Kongsberg and the GSFs. It does a lot of fairly lightweight checks, like making sure the dates included in file names match up with the dates encoded in the file itself, what datagrams are available in each one of these files, and it'll go through and not perform checks so much, but more sort of data extraction processes, like pulling out runtime parameters and installation parameters and position information, and just make that sort of information a little bit more accessible to users. Embezz grid checks, on the other hand, implements a series of checks that are run on gridded or processed bathymetry data, so the GeoTIFFs and the bag files. I guess the one gotcha there is that the Embezz grid checks require the data be provided in a sort of bit of a specific gridded format. So if you're using a GeoTIFF, we're going to need that GeoTIFF to include 3 bands, including the depth, the density, and the uncertainty, because we need all that information to run some of the checks, like density, for example. We need to know what the density associated with each grid node was. Lastly, we have find a GC, and we had some, I guess, internal sort of deadlines where we wanted to get a check going to identify flies in our gridded data sets and any holes in our gridded data sets as well. So to sort of support that, we utilized some code from QC tools as developed by HydroOffice, which you may be familiar with. So we took that code out, refactored, and ended up creating a new plugin for Find a GC that sort of supports those few checks. But I think the long-term plan that we're sort of thinking about with Find a GC is that it may actually be replaced by a QC Tools Quacks plugin that has a much better level of support for everything that QC Tools offers than Find a GC. But we'll see how that goes in the future. So you've seen the user interface mockups. We've gone through like the basics of what checks are implemented in Quacks. If you were to like leave this presentation and wonder, all right, how do I get started using Quacks? The best spot to go is the AusSeaBed website that we have listed there. The source code for Quacks is all up at GitHub, and like you'll be able to follow your way through using this link to GitHub if you want access to the source code. But there's so much more on the AusSeaBed website. We've got a link to the installation files, which you can just go and download. We have a series of tutorial videos. There's a short 5-minute one, and then there's a longer sort of 20-minute one. They both go into quite a lot of detail around how Quacks works in with existing bathymetry processing workflows. Importantly, there's a feedback form there. So what we're going to see on the next page is we're really interested in what the broader community thinks about Quacks in general. And the feedback form available on that website is one of the ways that we're sort of capturing that feedback. So definitely pay attention to that. If we talk about where Quacks is at the moment, we're very much looking at it's in a bit of a development hiatus at the moment. It's something that we will get back to, but it's not the primary focus of what we're working on at AusSeaBed currently. We are still definitely looking at supporting the user base, both existing and new users. So if you want to use Quacks and you have a question, by all means, get in touch with us. As I was saying before, we're very interested in your feedback. And we're working through this process of establishing a project governance. So it wasn't just AusSeaBed that created Quacks. We had quite a lot of input from NOAA and CCOM early in its development stage. So what we're trying to do is set up like a steering committee that sort of directs the future development of Quacks as a platform itself. Like what checks should we focus on? What new features should we implement? That sort of thing. So that's being set up at this stage. And once again, going back to what Danny was sort of talking about before, there's a lot of scope for including these sort of tools into automated processing pipelines. And that's one of the things that we'll be looking at getting Quacks to do in the short-term future. A bunch of other ideas I'd like to see implemented in Quacks, but we'll just have to try and find some time to get to it. So that wraps up my presentation. I'll open it up to questions.
Well, thank you, Lachlan. And still looking for our first question from the audience. Will one brave person step forward and submit a question. This is just a very shy group. Well, people know how to get in touch with our speakers, hopefully by email, in case they think of a question as soon as we end the session. I want to thank all of our speakers today, and like to note, we had a very wide array of time zones represented here. Our first speaker, Neil, was in South Africa. Danny is in New Brunswick, Canada, where it is very, very early in the morning. Satish is in India. Lachlan is in Australia. I am on the one edge of the Pacific Ocean, and our host for all of this, Aya, is on the other edge of the Pacific in New Zealand, and she's the one who's been making all these sessions work. So thank you, Aya, for making this all happen. Thank you, our speakers, for sharing your work with us today.